On April 21, Google engineers made headlines by publishing a groundbreaking research paper. They claimed to have conducted an experiment utilizing a 70-qubit Sycamore quantum processor. This revelation, reported by The Telegraph just days ago, has sent shockwaves through the tech ecosystem. Google's quantum computation, which took mere seconds, would have taken over 47 years on the most powerful supercomputer today. Google, who previously made waves in 2019 by announcing quantum supremacy, is once again thrusting the topic into the limelight. But what are the risks posed by these new quantum computers to modern cryptography? Is there a threat to Bitcoin and cryptocurrencies? These are the questions we'll delve into in this video. Before we dive into quantum computing, let's first revisit how our current computers operate. These machines already perform a plethora of astonishing tasks, but they communicate in a special language, much like a secret code. This language consists of bits. Bits, spelled BATS, are akin to the foot soldiers of a computer, electronic grains of sand. They can have two different values, either 0 or 1. Imagine these bits as tiny switches inside your computer that can be either off or on. Together, these bits collaborate to represent all the information that a computer comprehends, including numbers, letters, images, videos, and even sound. Visualize bits as building blocks. With them, the computer can reconstruct nearly anything it desires. Now, imagine giving a very simple instruction to your computer, like telling it to open a file. For your computer to comprehend this instruction, it must be transformed into a sequence of bits. For instance, we could say that this code means open, and this one, file. The computer knows how to interpret this specific sequence of bits to perform particular tasks. Modern computers have processors that handle billions of bits simultaneously, allowing them to solve complex problems, play video games, browse the internet, and more. This is the current state of affairs. However, classical computers remain relatively constrained when it comes to the number of bits they can simultaneously manipulate. To solve certain highly complex calculations, our current computers would need to operate for millions of years before finding an answer. In contrast, quantum computers can perform certain very specific calculations much faster. Instead of dealing with regular bits, quantum computers use quantum bits, also known as qubits. These qubits can hold the value of 0, 1, or a superposition of 0 and 1. It's this third possibility that changes everything. By utilizing this superposition state along with other quantum phenomena like entanglement and quantum interference, these new computers can disrupt the calculation process and consequently solve specific problems much more quickly. The concern lies in the fact that the security of modern cryptography relies on mathematical calculations considered difficult to solve for classical computers. In essence, imagine current cryptography as a gigantic lock with billions upon billions of possible combinations. In theory, it's possible to find the code by testing all the options one by one, but even with the most powerful current computers, it would take years. The time required to solve mathematical problems forms the foundation of modern cryptography. However, it's possible that in the future, these combinations could be cracked in acceptable time frames by quantum computers, which could undermine our current cryptographic standards. As the name suggests, cryptocurrencies are built upon these cryptographic methods. For instance, in the RSA encryption, a widely used asymmetric cryptography algorithm for e-commerce and confidential data exchange on the Internet, there are two options to decrypt a message. You either have the private key, which is the quickest way, or you attempt to solve a complex mathematical problem. In the case of RSA encryption, this involves factorizing large numbers into prime numbers. Prime numbers, for those who don't remember, are numbers divisible only by 1 and themselves. 2, 3, 5, 7, 11 are prime numbers. You can see them highlighted in red in this image, but there are infinitely many. Now, back to RSA encryption. If I give you the number 21, for example, and ask you to factorize it into prime numbers, you can quickly find the answer: 3 times 7 equals 21. But if I give you a 617-digit number, well, that's much more challenging. And that's precisely the principle of RSA encryption. If you have the private key to decrypt the code, no problem. However, with 100 digits, good luck finding the solution. The concept of cryptographic key size is crucial. For a robust algorithm like RSA, as soon as the key size is no longer sufficient to ensure encryption security, you move to larger keys. When those are no longer sufficient, you transition to even larger keys, and so on. This is how cryptography maintains its security despite the improvement in computer power over time. The relationship between key size and the time it takes to crack the code is described using algorithmic complexity in computer science, and Big O notation is employed for this purpose. This graph illustrates the relationship, with the key size n on the x-axis representing the combination size of the lock. How long would it take to break the algorithm? Today's best computers fall into this white zone. So, as you increase the lock's length, the difficulty of finding the code increases almost exponentially. Now that we've covered this, we can quickly see the problem quantum computing introduces. Recall my introduction. I explained that quantum computers are intriguing because they parallelize calculations. This also means they could significantly reduce the number of operations needed to solve the mathematical problems at the core of cryptography. In fact, there are already several algorithms designed specifically to accelerate these calculations on quantum computers. The two primary threats to modern cryptography are Shor's and Grover's quantum algorithms, invented in 1994 and 1996, respectively. Yes, the quantum threat is not new. Shor's algorithm affects asymmetric cryptography, while Grover's is efficient on hash functions and symmetric encryption methods. However, let's focus on Shor's algorithm because it could genuinely pose future problems. It's designed to factorize integers into prime numbers. The same challenging problem we discussed earlier, but much faster. This means that the computation time required for the task reasonably scales with the size of the number to be factorized. In simpler terms, increasing the lock size doesn't buy you much against a quantum computer. As shown in this graph, quantum computers would reside in the black zone. For a given key size, Shor's quantum algorithm could solve the computation and break the encryption much faster than a classical computer. Let's take an example. If you wanted to break a 2048-bit RSA private key with a classical computer, it would require performing an astronomical number of attempts. In essence, it's impossible. Now, if you had a quantum computer, Shor's algorithm could crack the same key in just 6 billion operations. That's still a large number, but it would be feasible in a matter of hours or days. However, don't panic. Even if Shor's quantum algorithm exists and works in theory, we are still far from executing it on a quantum computer. Yes, quantum computers already exist, and you can even try some for free on the cloud. However, they are still far too limited to successfully run Shor's algorithm, and there are numerous reasons for this. For instance, you would need a quantum computer with a vast number of qubits, which doesn't exist yet. Furthermore, to perform calculations as complex as those required by Shor's algorithm, qubits would need to maintain their quantum state long enough. Current quantum computing performances are far too unstable, and information would be lost before all the required operations could be completed. In summary, quantum computers are indeed functional, but at this point, it remains highly experimental. Quantum computers operate in a closed-circuit environment with no interaction. Place them outside of their carefully controlled setting, and they become lost. In the short and medium term, there doesn't appear to be a significant threat to cryptography, including Bitcoin and cryptocurrencies. This seems to be the consensus among experts, as demonstrated by a 2022 survey of 40 industry professionals. In this study, experts were asked about the likelihood of a quantum computer breaking a 2048-bit RSA private key in 24 hours. Without delving into the details of the survey, the key takeaway is that in the short and medium term, there doesn't seem to be a significant risk to cryptography. However, in the long term, concerns are more legitimate. Now that we've identified and assessed the problem quantum computing poses to cryptography, we can ponder whether these risks also apply to Bitcoin and cryptocurrencies. In Bitcoin, as you likely already know, two main cryptographic methods are used: hash functions and digital signatures. Concerning hash functions, primarily employed in mining, such as SHA-256 for Bitcoin or the previously used Keccak-256 for Ethereum, there doesn't initially appear to be a risk. Based on current knowledge, these hash functions are expected to be minimally, if at all, affected by quantum computing. I won't delve into the details here, you'll need to take my word for it, but I encourage you to research this further, starting with the articles I'll link in the video description.